helicopter repairmen acquire a thorough knowledge of the operation of each and every component, so that the high degree of dependability designed into these hydraulic flight control systems is not lost through improper maintenance.
This is Vietnam War vintage.
Are vital to the operation of all aircraft. Wing and tail control surfaces, landing gears, arresting hooks and other aircraft components are dependent upon properly functioning hydraulic systems. As with any system dependent upon working parts, malfunctions sometimes occur.
How about that?
When this happens, you must find out what's wrong before you can correct it. This is called troubleshooting. No matter how simple or complex the job, no matter what type of aircraft you fly, there are 7 major steps which you must follow in troubleshooting. Conduct a visual inspection. Conduct an operational check. Classify the trouble. Isolate the trouble. Locate the trouble. Correct the trouble. Conduct a final operational check. Before we take a closer look at all 7 steps, let's consider 2 important things that you must first do before you begin to troubleshoot. Familiarize yourself with the aircraft's characteristics. Do this by consulting the handbook of maintenance instructions, or in the case of newer model aircraft, the maintenance instruction manuals. You're not required to memorize complete aircraft systems, but you must know where to go for the answers. The second thing you must do before beginning to troubleshoot is to conduct a thorough safety check of the aircraft. Even though the aircraft was supposed to be secured, you must personally double check. Are the ground locks properly installed? If they hadn't been, and someone accidentally actuated the landing gear during troubleshooting, $250,000 aircraft would hit the deck. And what is even worse, it would take along anyone who happens to be working underneath. Check the cockpit to be sure all control systems are locked. After checking the jury struts and satisfying yourself that the aircraft is safe to work on, you can go to the first step in troubleshooting. Conduct a visual inspection. The main reason for conducting a visual inspection is to find obvious reasons for malfunction. For example, it has been reported that the wing fold system is not operating properly. This system, like all others, has various elements strung out in a long sequence from the cockpit to the mechanism itself. When you start out, you can't be sure where the trouble is or what the nature of the trouble is. Even in a hydraulic system, it could be something mechanical, like this. If you do find a discrepancy, whether or not it contributed to the original malfunction, correct it before proceeding. Check the hydraulic lines and fittings. See if there's evidence of leakage. If so, check for loose fittings and tighten on the spot. Now clean up. Not so much for good housekeeping, but to make it easier to detect any further leakage. And don't rule out the possibility that the trouble can be electrical. A broken safety wire is a good indication that a loose electrical fitting may be the cause of the malfunction. This condition, like the others, can be corrected on the spot. Make sure you replace the safety wire to prevent the fitting from becoming loose again through vibration. When all obvious discrepancies have been corrected, you can proceed with your troubleshooting without further harming the aircraft. Conduct the operational check. There's a good chance the visual inspection didn't eliminate all the trouble. The only way to find out is to operate the system. The system should be operated using the aircraft's own source of hydraulic power. In some cases, you could use external power, but then you run the risk of bypassing some component that could be causing the malfunction. See if the system functions properly, making sure you observe all normal safety precautions. In this case, momentary actuation ensures that all wing fold components are in proper position. Now, you can safely spread the wings. A complete system cycling, such as this, will tell you if the discrepancy has been corrected in the visual inspection, or if it still remains. So far, everything works all right. Now the trouble is apparent. One lock pin has not extended. The malfunction is still there. And it is also evident that the corrective maintenance required will be extensive enough to warrant moving the aircraft into the hangar. While the line crew secures the plane for towing, you can proceed to the third troubleshooting step, which will take you back to the books again. Classify the trouble. In this step, you determine the type of trouble in the system, whether it is hydraulic, electrical, or mechanical, or a combination of these. To classify the trouble, refer to the troubleshooting section of the handbook for the specific system in question. In most cases, you will find the identical malfunction listed in the trouble column. Directly alongside are listed the probable causes of the failure. In this case, there are two possibilities. The stops in the center section wing fittings need adjustment, or the wing lock cylinder is stuck in a retracted position. In the final column under Remedy are the steps required to correct the trouble. This one is classified mechanical, and this one is hydraulic. At this point in your troubleshooting, you don't know whether it's one or both. Isolate the trouble. In other words, pinpoint the location of the faulty components. No matter how familiar you may be with your aircraft, use the schematic in the handbook to isolate the components, not the aircraft itself. The schematic shows where the components are located in relation to the overall system. System descriptions that accompany the schematic tell you exactly where the components are situated in the aircraft. In many cases, within an accuracy of 1 inch. With your homework completed, you are now ready to return to the aircraft and finish the job. Locate the trouble. In this step, you narrow down the possible causes to the faulty unit or part. When returning to the aircraft, remember to take all the tools and special equipment necessary to completely locate and identify the trouble. And, most important, don't forget your handbook of maintenance instructions. Now you are going to check out the 2 possible sources of trouble using the process of elimination. First, rule out the relatively simple cause. In this case, see if the stop is correctly adjusted. To do this, you will have to see if the lock pin starts to extend under normal hydraulic pressure. Hooking up a hand pump greatly simplifies the power requirement. Simulate the outer wing panel fitting by using a stop adjusting block. Align the hole with the locking pin using a locating pin. Now apply the power. Notice that all the lock pins extend except the pin with the malfunction. Had it started to extend, the problem would have been mechanical, which could be corrected by simple adjustment. However, its failure to move indicates a hydraulic malfunction in the lock cylinder. Correct the trouble. Remove the defective parts and either repair them or obtain new ones. In this instance, you must remove the defective wing lock cylinder. Whenever you must replace a component, refer to the procedures outlined in your handbook of maintenance instructions. Experience has proven that the fastest way to get a job done is to go by the book, step by step. Even though you may have replaced hydraulic components time and again, take time out to refresh yourself. It will save time and material in the long run. When the job is finished, check to be sure that all lines are tight and that the component is mounted securely. Make sure you don't leave any tools on the aircraft. and particularly not inside the wing bucket. Now is the time to practice your housekeeping. Wipe off all hydraulic fluid and clean up any other mess you may have created. You are now ready to move on to the last step in troubleshooting. Conduct a final operational check. Of course, this is done to be sure the original malfunction has been corrected and that there are no new ones. The aircraft is restarted. Don't overlook the safety check of momentarily actuating the system to prevent components from operating out of sequence. In all troubleshooting, whenever a component is changed, you are required to conduct 3 cycles of operation for a complete check. In this instance, the wings must be unfolded, locked, and folded again 3 times. The reason for this is twofold. First, to make sure that the new component is functioning properly, and second, to purge the system of all trapped air. Each time, as the final operational check proceeds to the point where the trouble was first apparent, pay particular attention to the system to make sure it now works properly. As you see, it does. In this film, you have seen the 7 major steps which you must follow in all hydraulic troubleshooting. These steps not only enable you to track down and isolate a system failure logically, methodically, and rapidly, but also serve to protect you and the aircraft you maintain. Let's run through them again. Conduct a visual inspection to find obvious reasons for malfunction. Conduct an operational check to determine if all the malfunctions have been eliminated during the visual inspection, or if there are additional discrepancies which will become apparent in operating the aircraft. Classify the trouble to determine the type of trouble in the system, whether it is hydraulic, electrical, or mechanical, or a combination of these. Isolate the trouble to find the precise area of the malfunction. Locate the trouble to identify the actual unit or part causing the malfunction. Correct the trouble by removing the defective parts and repairing them, or turn them in and replace them with new parts. Conduct a final operational check to be sure the original malfunction has been corrected and that there are no new ones. Remember, the 7 troubleshooting steps remain the same for each type of aircraft. Helicopters, transports, ASW aircraft, fighters, and attack. The work you perform on the hydraulic systems of these aircraft directly affects the safety of the men who do the flying.
Okay, what I've got for you is maybe just a little bit of summary of a little bit on troubleshooting. We'll talk a little bit first about system division. In class, we went through a lot of the component parts that make up a typical hydraulic system, but it breaks down this way really for a lot of the systems. We have items that are considered part of the power control group in aircraft or hydraulic systems. We have directional control, and then we've got actuation. the end result of what we're trying to do by moving an actuator is really accomplished by item 3, the actuators. But let's talk a little bit in detail about all of these. By the way, these refer to primarily closed center hydraulic systems. Seldom in modern aircraft do you see anything open center, but logical groups anyway for closed center systems. Power control, this begins at the reservoir, and it includes all things including the pumps, either engine driven or electrically driven. It doesn't matter if it's constant displacement or variable displacement, and it also includes the accumulator. So all the things that are responsible for providing the push and regulating the flow of hydraulic fluid are included in that group, including the reservoir. Auxiliary hand pump, if there is one, the secondary power pump, ram air turbine, or power transfer unit are also included in that group. So that's everything that really provides power. By the way, by logic, many of the schematics develop the schematic from left to right. So when you look at a schematic, usually at the left-hand side of the illustration or diagram, you'll find those components are located at the far left. Next comes directional control. So we've talked about selector valves and solenoid selectors and servo valves that are dependent upon initial movement of a pilot valve. But these include selector valves, solenoid selector valves, and I guess also the pilot valve that might be in a servo actuator. So now you're diverting hydraulic flow into the component from the power control area. And then lastly, actuators. Double and single acting, you know what those mean. We either got hydraulic fluid that alternately moves a component in either direction, or we've got a single acting actuator that uses some method other than hydraulic fluid to push the actuator in one position. It also includes actuators that are either full travel or they're positionable, like hydraulic flight controls wouldn't necessarily be full travel type actuators. They're considered to be positionable. Landing gear, on the other hand, are full travel type actuators. They're designed to be in one of two positions. And also included in that group for actuators would be hydraulic motors. These are rotary actuators, so when we have to develop rotary motion, we'll either use a V-type actuator or we might use a piston-type hydraulic motor in order to be able to get rotational motion. Some of them are reversible. For example, if we've got a stabilator that would be hydraulically controlled, a lot of the stabilator actuators are driven by a hydraulic motor that's reversible. And some of the hydraulic motors are also speed or torque governed. Some motors, they use a flow regulator at the inlet of the device in order to control system flow, so that kind of controls the speed of it. Other hydraulic motors are governor controlled in order to get you something that you're trying to look for. You're trying to drive a constant speed drive, or maybe a generator at a particular frequency. So they'll have a torque governed type of motor in order to drive them. But this is the basic breakdown for most hydraulic systems for power control, directional control, and actuation. That's it. What you saw also from the movie, what I did for you is I broke down all of the steps that are required in troubleshooting. Even though that video seemed kind of simplistic and old, it was still valuable. There's so many things that were in that thing that are worth noting, even for modern aircraft. For a lot of things that are hydraulic or electrical or mechanical, your job in troubleshooting is to ultimately be able to isolate the particular problem and solve it. And you've got a particular problem working as a technician or a mechanic in the field. You don't have the luxury that the manufacturer does of just kind of swapping out parts in order to see that something will make a component or make the system work. When you're working in the field by yourself, you're going to have to be able to figure out what's wrong on your own. When I was at Sikorsky, there was a lot of shotgun troubleshooting, but they could afford to do something like that because they had multiple components that they could take off of a production rack and try to correct a problem that might develop as an aircraft is going to be ready for delivery. But you as a mechanic don't have that luxury. You've got just what you have, and you have to be able to adequately be able to isolate the problem and correct it. First thing you saw in the video was a visual inspection. Things that can be initially indicated as not quite right, you can fix. For example, that broken piece of safety wire or the fair lead that was on the opposite side of the control cable. we can fix some of those things, but we'll take note of that first and maybe make those corrections initially. An operational check, you don't know exactly what's wrong, and so you're going to have to figure out what's going on. This is where it's important to know what normal is for a hydraulic system. If you have no indication of what normal is, how can you ever figure out what's wrong? So for example, when you turn or flip a switch on or position a control on an aircraft, what is supposed to happen? So again, an operational check in order to kind of verify what's wrong. But again, you have to know what normal is before you can even begin. Otherwise, you have no idea really what the problem might be. You'll have to classify the trouble. You saw in that video. The problem with the wing fold system could have either been mechanical or hydraulic. And one particular case, if it's mechanical, it required maybe adjustment of that particular stop in order to make it function correctly. And the hydraulic portion of it, well, that involved verification that hydraulic pressure was able to move the lock pin into the closed position. That case warranted replacing the actuator or the lock pin actuator if it was wrong. But up to that point, it could have been either thing. So you're going to have to classify the particular problem. Isolate it to one or the other. Locate the trouble. So again, you find that the lock pin, in fact, is the actual problem. Correct it. In this case, what you saw in the video. They replaced that lock actuator in order to correct it. And the final operational check, you're verifying that everything has been corrected. And additionally, you're also purging any air that might be in the hydraulic circuit out. Many of the hydraulic systems are self-purging of air through repeated operation because you're returning the hydraulic fluid and air ultimately back to the reservoir where the air is finally purged of the hydraulic fluid. But these would be the common troubleshooting checks. Visual inspection. Inspection should be thorough and searching to include section of all lines, units, mechanical linkage, components of evidence of leaks, looseness, security, material condition, proper installation. During this visual inspection, the hydraulic system should be checked for proper servicing, the reservoir for proper level, and the accumulators for the specified preload. So again, you're looking to verify that what is there is technically correct as best you can make it. So visual inspection is first. Next, operational check. It says the malfunctioning system or subsystem is checked for proper operation. This is normally accomplished by attaching support equipment to the aircraft, which supplies a source of electrical power and pressurized fluid to operate the hydraulic system. In some instances, however, the aircraft may be ground checked directly by using aircraft powered equipment. Depending upon circumstances during the movement of a malfunctioning unit, the mechanic checks for external leakage, the correct direction of component movement, its proper sequence of operation speed, whether or not the complete cycle was obtained. Remember also, they pointed out in that video that it's possible to sometimes overlook a problem as a result of not using aircraft supplied power. If you're using a ground power unit to substitute for maybe an aircraft pump or maybe for an electrical source of power, you're bypassing a portion of the normal circuit or the controlling circuit for what you're inspecting. So you may overlook a problem as a result of not using aircraft power, either electric or hydraulic. So, okay, so that's the operational check. Classify the trouble. Malfunctions usually fall into one of four basic categories: hydraulic, pneumatic, mechanical, or electrical. By using the information gained from steps 1 and 2 and above, the technician can determine under which classification the malfunction occurs. So now you're classifying it, you're further working down your way through like a trouble tree in order to figure out what's wrong. Oh, by the way, too, a lot of manufacturers use trouble trees for troubleshooting. That's a very difficult, laborious task to actually create one. I work with some very skilled and talented people at Sikorsky that did a pretty good job in developing trouble trees. You have to have a basic idea of what's most probable in order of importance that might potentially fail to work on a trouble tree and get one into a service manual. Isolate the trouble. Step calls for sound reasoning and a full and complete knowledge of hydraulic theory as well as a complete understanding of the affected hydraulic system. During this step, you must use your knowledge and the known facts to determine where the malfunction exists in the system. Usually the trouble can be pinned down to one or two areas, eliminating those units that could not cause known symptoms and those can be proved to be operating normally will usually identify the malfunction. Sometimes too, you'll see maybe perhaps you can't operate an actuator with the normal hydraulic power pump uses a source of pressurized fluid. However, the same component can be operated maybe with a hand pump. Well, again, two sources of potential pressure that might obviously be used to operate the same component. Well, you know from a lot of hydraulic systems, if you've got a low reservoir, the hydraulic pump is starved of fluid, and because of the standpipe that's in the reservoir. So if that particular circuit is operational using the hand pump, really the fix to that kind of problem is simply nothing more than adding fluid and replenishing the fluid in the reservoir. And miraculously, the problem is solved. But again, you might have noted that, you might have fixed the problem inadvertently because during the the initial inspection steps, servicing the reservoir to the correct level may have already corrected the problem. So isolate it anyway. Locate the trouble. This step is used to eliminate unnecessary parts removal, thus saving money, valuable time, and man hours. Often you must determine which unit or units in the system could have caused the malfunction, thus verifying the isolation step. So what we're trying to avoid is shotgun troubleshooting. We're trying to narrow down our choices of what might be wrong down to one thing and one thing only. The diesel instructor gave me some sage advice. He said, never replace a component until you can specifically identify that that component is the problem. Otherwise, you're just kind of chasing your tail in a circle to solve something that's wrong. Years ago, I might have mentioned this to you in class. I had a problem with fuel starvation in an automobile, and finally the engine finally quit. It was an old car that I was operating, and it had done it a couple of times, and I just assumed that the fuel pump was wrong. Was bad in it. And I went through, I think, a couple of mechanical fuel pumps before I finally realized that the pump wasn't the problem. The problem was that the vent opening at the fuel cap had been blocked by dirt. So I went out to the fuel tank, opened the tank up, and I heard this rushing sound of air entering the tank, and all of a sudden I realized what was wrong. So those two previous pumps I did really did nothing to solve the problem. Really all it was a little bit of collected dirt that was in the fuel tank cap and the vent opening that developed a vacuum on top of the fuel, and of course the pump can't overcome that, so the engine stopped. So I learned my lesson. Correct the trouble. This step is accomplished only after the trouble has been definitely located, and there's no doubt that your diagnosis is correct. Malfunctions are usually corrected by replacement of units or components, rigging and adjustments, and bleeding and servicing. Correct the trouble, conduct a final operational check. The affected system must be actuated a minimum of, it says 5 times, but again, that's more of a military rule. Just verify that the system works correctly and it's actually been purged of air. And made to determine that the operation adjustments is satisfactory. And again, troubleshooting highlights, again, systematic approach whenever we're trying to solve problems. You have to look at the system overall. And a big advantage is having the correct service manual that you're using for the aircraft. Sometimes too, the manual I think kind of plays a big role in it. Certainly there's exceptions you might find, but if you've got the manual in hand, sometimes it's a big step in being able to understand what's wrong. Also, time is your best friend and it's your enemy. A lot of times when you go to troubleshoot, it's under a condition maybe where the aircraft has to leave immediately. Well, man, you're under the gun trying to figure out what's wrong. Sometimes it pays to familiarize yourself a little bit with the aircraft and its system so that maybe when something develops, you have an idea of what might be wrong. As I mentioned, no one understands what normal operation is. If you don't know what normal is, how can you determine what's not really quite right or not abnormal? So what should happen when an actuator moves into a certain position or you turn a component on or off? Is there supposed to be a certain amount of time for the component to actuate? How long? Is normal leakage anticipated? How much? So again, you should know what normal is in order to be able to figure out what's wrong. Number 2, have available all schematics prior to troubleshooting. Schematics are very frequently show direction of fluid flow. It's almost impossible to troubleshoot complex systems without one. So otherwise, you're just standing inside of a wheel well area or a servicing bay, and you're looking perplexed, and nothing is going to solve that. You're going to have to have available all whatever literature that would be required in order to be able to troubleshoot. You have obvious things, like leaking fluid and that sort of thing, but If it's not that, something that visibly detectable, you're gonna need some literature. Isolate the subsystem first and individual components one at a time. Assume only one failure at a time. So again, in that troubleshooting list of things that you're supposed to look at, we don't assume all mechanical or all electric, mechanical, and hydraulic at the same time. You're going to have to do further isolation to be able to figure out what's wrong. Logically reason that replacement of a component will solve a problem before the component is replaced. So again, from the diesel department, which is also applicable to what you do here, if you can't prove in your own mind that replacement of that component is going to solve the problem, you better not take it out. Okay? You may not be able to get a replacement. Again, avoid check-in troubleshooting. It's unproductive, it's expensive, and it wastes a lot of time. Sometimes, things that aren't readily apparent will cause a problem. In manufacturing of aircraft, somebody is careless with a pneumatic drill and they put a drill bit right through a cable, or at least a bundle of wires. So sometimes you find that by twisting a bundle of wires, that you've got either a broken or a shorted connection. And again, it was simply caused by somebody kind of carelessly doing things in the aircraft. But again, just kind of haphazardly replacing equipment, you're not doing anything to help yourself. Consider the most likely component or item to fail first in a list of potential components and check the easiest items first. We're going to look at the reservoir, we're going to look at the accumulator, and we're going to figure out if those things are in a normal condition. So again, look at the quantity of fluid in the reservoir, make sure that the actuators are maybe in a neutral, or at least the controls are in a neutral position for flight controls, and check the condition of the accumulator. So kind of do the easiest things you can first. Use and verify conditions using aircraft instrumentation where possible before using shop equipment. And again, there's always the danger of bypassing something as a result of using some ancillary piece of equipment. The aircraft has got an ammeter on it. It's a handy device for troubleshooting. A lot of cases when things are drawing a high load of amperage, it indicates a component either misrigging or failure. A good example would be, for example, like on some landing gear systems. Obviously, if there's a lot of misalignment in the landing gear retraction system on some aircraft that have electrical gear, the motor is drawing more current than what might be considered to be normal. Well, that could be detected by looking at how much amperage is being drawn during retraction and extension and comparing it with, again, what normal is. But again, first, you're going to have to figure out, or at least know what normal should be. So anyway, we want to use what the aircraft has aboard it before we do anything else. Let's see. I'll kind of cut right. It's what, 7? It's 5:30 or so. Why don't we take a break for a half hour and come on back? Okay.